Before we can really begin to understand waves, we have to understand what type of motion creates waves in the first place. And that kind of motion is called periodic motion. And that periodic word means that the motion is repeating itself at regular periods of time, or regular intervals of time. In other settings in physics, this is also sometimes called harmonic motion. In general, though, really all of these motions could also be called vibrations, because we're going to talk about how each particle is going to be essentially vibrating back and forth around some reference point, moving in one direction and then back in the opposite direction, back and forth repetitively. And so we're going to call those vibrations, and we can actually split those up into three basic kinds of vibrations. So the first kind is called a transverse vibration. And that word transverse has to do with perpendicular. So in this case, it's when an object is vibrating perpendicular to its axis at the rest position. So what I mean by that is, in this case, in this picture that you see, this dotted line here is its rest position. That's where the particles would be. If you imagine this was a string and there was no waving of this string, the particles in the string would just be nice and flat along that line. But then as soon as I start to wave that string, all the particles in the string move. And it's going to look like the energy of the wave, these crests in the wave that we see, will move down the line in that particular direction. So that's why down at this end you can see velocity of propagation is a fancy way to say that's the way the wave energy is going to move. But each individual particle in the string is not necessarily doing that. So if I identify one particular particle, let's say right there in the string, it's actually not going to move left or right at all. What it's actually doing is moving straight down and then moving back up. And when enough of those particles do a particular pattern of moving down and up, but in a staggered way, it will appear that the motion of the actual wave is moving down the line towards the right in this case. That's a transverse wave. So each individual particle is vibrating up and down, for example, while the wave moves left to right. So the rest axis and the particle's movement is perpendicular. The longitudinal wave is a little bit different. And we're going to talk even more about this when we get to the sound portion of this unit, because sound waves are actually longitudinal waves. In that case, we still have a wave pattern that is moving in a particular direction, so that's what that arrow along the bottom is representing. So this wave would be moving from left to right. But each individual particle, and really these lines are all representing an individual particle, but we can imagine just identifying one particular particle in that line. It's actually not moving up or down. It's going to move a little bit towards the right and bunch up in what we call a compression, but then it will naturally spread itself back out because there are often kinds of forces that will pull it back towards its rest position. So it will swing back towards its rest position. So you can imagine if this was a spring, for example, it could swing to the right a little bit, but then it would get stretched back and pulled back towards the left. And so it's actually just going to go back and forth, left to right, back and forth, back and forth. So at certain points, when it scrunches together, when all of the particles get bunched together, we call that a compression. In other areas, though, where the particles get naturally more spread out, we call that a rarefaction. Now, this becomes a little bit easier to visualize when we actually have a moving picture of what's going on. We'll talk about the last example in just a second, but we can try and understand transverse and longitudinal waves a little bit better by looking at the case of a slinky. So this is what a slinky could do to represent a transverse wave and a longitudinal wave. So if you just focus in on one particular part of the transverse wave, if we focus in maybe in this area, you'll notice that it's going up and also going down. But the energy of the wave overall clearly makes it look like it's moving down the line to the right. So each individual piece of the thing making up the wave is just going up and down, but the wave's energy is moving towards the right. So that's a transverse wave. But look at how that's a little bit different in the longitudinal wave. If I identify one particular spot, let's say right about here, you'll see that particular area swing towards the left and then swing back towards the right, back to its rest position. And because it's swinging back and forth left to right, in certain areas that's causing it to bunch up, that's the compression part, and then other areas get more stretched out or spread out, and we call that a rarefaction. And the final kind in our chart is called a torsional wave. So let's backtrack here to our chart. So a torsional wave is a little bit more complicated to understand its motion exactly, and we're not going to deal with it a lot in this course. But for reference, it is just when an object is twisting around an axis at its rest position. And so in this diagram here, this line that's going through the middle is like a bar that all of these other bars are lined up connected to. And each of these bars can swing in one direction and then down in the other direction. And so they are all swinging and transferring their energy down the line, so that really, instead of just going up or down or left or right, what's really happening is each particle is twisting back and forth. And again, that's much easier to visualize when it's actually moving. So this would be a torsional wave. And we're actually going to build a wave machine very similar to this a little bit later in this unit. And so in this particular case, this gray line that you see that I've just highlighted in red there, that is the bar representing the rest axis that it's all twisting around. And to create a wave machine like this, you just need to attach a bunch of bars to that central bar, for example, these ones here. And the lines that I've drawn represent what their rest position would be. And you can see they twist back and forth from that rest position. But as soon as one of them twists, it transfers that twisting energy down the line. And so the wave, even though it's just twisting back and forth, the wave energy moves in that direction until it reflects and comes back in the other direction. We'll review those in a little bit more detail in class as well, but we should also talk about some important terminology that's involved with periodic motions, and a lot of this same terminology is going to be used when we talk about waves more generally. So the first one that's important to understand is amplitude. And amplitude, the definition you have there is that it's the maximum distance from the rest position made by a vibration. The easiest way to show this is actually if I just go back up to the top of my note and just demonstrate that from the highest point or the farthest away from the rest position that this particle could reach, and this represents the rest position, the distance in between these that we measure is the amplitude. So that is your amplitude there, the maximum possible distance that a particle could move from its rest position. So in a transverse wave, it's that line that I've just drawn in. That's the amplitude of a vibration. And we'll also use that term when we talk about amplitudes of a wave. Period, we use a capital letter T to represent it. And that capital T, though, is still just a kind of time. Instead of using a lowercase t, though, like we've normally used for time, we're going to use the capital T because it's a very special kind of time. It's in particular the time that's required for just one cycle of a vibration to occur. So if we just measure how many seconds one vibration occurs in, that is the period. And sometimes it might be a very quick vibration, so we might have a very small number of seconds. The frequency is actually the opposite. Instead of the time it takes for one cycle, it's the number of cycles for 1 second. So frequency, again, is just the number of cycles that can be completed per each second that goes by. And we actually measure that in the unit we'll talk more about in class. If we're taking a number of cycles, which doesn't really have a unit, it's just going to be some number of cycles, we take that number and then we divide it by a unit of seconds. So our overall unit actually gives us something a little bit weird. Our overall unit is just 1, or the standard number, divided by seconds. So instead of writing 1 over seconds, we use a new term and we call it hertz. So 1 hertz is 1 cycle per second. That's the other way to say it. If something is 50 hertz of frequency, that means it completes 50 cycles in 1 second. That's the idea. Phase is another concept that we'll talk more about in class, but in general it's just describing how lined up two crests are. And so when we draw vibrations as waves, certain motions involve a crest. And we'll talk about how they can line up with one another And if they are lined up, we'll say that they're in phase. When they're not lined up, we'll say that they're out of phase. And in class, we'll draw a couple diagrams to really demonstrate what this means. So for now, don't worry too much about it. One last fact that we can point out, though, that's really handy to know, is that frequency and period are strongly related to one another. In fact, they're exact inverses of one another. One of them is the number of seconds that it takes for each cycle. The other is the number of cycles that can be completed each second. And not only are they logical inverses of one another, they're also mathematical inverses of one another. And what that means in math is if two things are inverses, we can find the other as long as we know one of them. So for example, if we are told what the frequency is, or actually I should say if we are told what the period is, we can use it to find the frequency. And the other way around, if we are told what the frequency is, we can use it to find the period. And all we have to do to find that inverse value is do 1 divided by the value that we have. So if we want frequency, we can take 1 and divide it by the period. If we want the period, we can take 1 and divide it by the frequency. There's another way we could think of this, though. Sometimes, if we're trying to find frequency, we might not actually know the period, but we might be told how many cycles something completes and how long it took to complete those cycles. So the other way we can think of frequency is it's a number of cycles divided by the time that it takes to produce those cycles. And so that will tell us how many cycles it can complete in just 1 second. If we are trying to find period and we don't know the frequency, but we're just told how many cycles something completes and how long it takes, we can do the opposite. We can say that the time for just 1 cycle is going to be the time overall that it took divided by the number of cycles that were completed. So in general, they are mathematical inverses of one another, but if you're not given one, you can't find the other. So sometimes we need to use just how many cycles are completed and the total amount of time that it took to find those cycles in order to solve. And in class, we'll do a couple quick examples to demonstrate how that goes.